Imagine a group of people trapped in a cave since birth. They are unable to explore and experience the world beyond its confines. All they could do was stare at the wall in front of them. They've never seen the world outside. They don't know sunlight, colors, or life beyond this dark, enclosed space. Behind them burns a fire, and between this fire and the prisoners is a narrow walkway. When people pass by, shadows flicker across the wall, creating moving shapes. To the prisoners who know nothing else, these shadows are all they believe to be real. They hear sounds and assume they come from the shadows themselves, unaware that what they see is only a faint reflection of reality, mistaking these illusions for the entire truth. This is Plato's allegory of the cave. And it's not just an ordinary story. It's a way of looking at our lives, our beliefs, and even our entire understanding of reality. Think about it. Those prisoners weren't stupid or ignorant, they were just stuck in a situation where their entire world was based on shadows, echoes, and incomplete truths. How different are we really from them? You're convinced that the world you see is all there is, but what if it's not? You're surrounded by information, yet how much of it is truth? You're confident in your freedom, but are you really free? You're comfortable, but comfort is dangerous. You're part of the story, just like the prisoners. The question is, will you ever dare to leave the cave, or are you too afraid of what you might find? Imagine you're standing by a lake. You toss a pebble into the water and ripples spread out across the surface. You watch as the patterns shift and change, and it all feels simple, cause and effect. You're an observer, and you've just witnessed a simple interaction in physical reality. This is easy enough to understand, but what happens when we start to include consciousness, the subjective experience of being and perceiving, into the equation? Science, and in particular physics, has always focused on objective realities, things that exist independently of our minds. This approach seeks to understand the universe through measurable, reproducible phenomena that exist independently of human perception. It's based on the idea that we can measure and understand the world without letting our personal biases get in the way. But there is a problem with this idea. It excludes the ability to describe subjective experiences. Objective reality is defined as something that exists independently of the mind, but whose mind is it independent of? Without acknowledging the existence of a subjective mind, the very foundation of science becomes contradictory. Science is built on the idea of observable facts. If you drop an apple, it falls. This action is true for everyone, everywhere, and every time. For centuries, this was easy to accept because the world appeared to behave the same way no matter who was watching. If you drop an apple, you see it fall just as I do. The consensus reality allowed us to create a common understanding of the world, one based on objective measurements. But when you pause to reflect, the idea of objectivity starts to feel a little strange. We've built an entire system of physical science that, at its core, relies on an observer to give it meaning. All the concepts of physics are tied together in a huge mathematical framework, but this framework doesn't connect to anything tangible except through its relationship to the observer. So we should have known all along that objectivity was an imperfect idea, but we didn't really, until it began to crumble with the advent of quantum mechanics. This branch of physics disrupted the notion that all observers experience the same reality. It shattered the comforting illusion of an independent, universal reality and revealed that the observer, the subject, doesn't just passively perceive reality, but actively participates in shaping it. Quantum mechanics suggests that reality can depend on the observer, challenging the idea of a universally consistent, objective reality. One of the most famous examples of this is the double-slit experiment. Imagine a beam of light or a stream of particles, like electrons, being shot at a barrier with two slits. When the path of the particles is not observed, they exhibit wave-like behavior, creating an interference pattern on a screen placed behind the barrier. However, the attempt to observe which slit each particle passes through collapses the wave-like behavior, forcing the particles to behave like discrete particles. This intriguing result suggests that the act of measurement itself alters the outcome, as if reality decides how to behave based on whether it's being observed. Another example is Schrödinger's cat, a thought experiment that takes this idea to a much larger scale. Imagine a cat in a sealed box with a mechanism that has a 50-50 chance of killing the cat, based on the decay of a radioactive particle placed within it. According to quantum mechanics, until the box is opened and someone observes the cat, it exists in a strange state of both being alive and dead at the same time. The cat's fate is only determined when you look inside, highlighting how the act of observation influences the state of reality itself. We talked more about this in one of my previous videos. The link would be in the description. In the quantum realm, particles can exist in multiple states or locations at once until observed, settling into a definitive state. The observer's act of measurement directly influences the behavior of these particles. This challenged the already unstable foundation of the idea of an objective reality. In other words, quantum mechanics suggests that reality doesn't have a fixed, definitive state independent of observation. It's as if the act of observation brings reality into existence. This doesn't mean that observation creates reality, a common misunderstanding, but rather that observation plays a key role in determining how reality presents itself to us. If we take this perspective, it's easy to see that objective reality doesn't exist. There's no singular, fixed version of the world that exists independently of observation. Instead, what we think of as reality is deeply tied to the way we observe and interact with it. Despite the evidence from quantum mechanics and relativity, many of us still believe in an objective reality. It's comforting to think the world exists in a certain way, unaffected by our perception. But this belief isn't just outdated, it actively limits our ability to understand the universe as it truly operates. The concept of objectivity served us well for a time, but it no longer fits the realities described by quantum mechanics and relativity. Clinging to it is like the prisoners in the cave, staring at shadows on the wall and believing they are the entire truth. Just as the prisoners couldn't see the fire or the objects casting those shadows, we're limited by our perception, mistaking an incomplete picture of the universe for the whole. Questions like, how or why does quantum physics work? Or what do the mathematical structures in quantum theory actually represent, often reveal more about our own assumptions, biases, and ways of thinking than they do about the universe itself. These questions are shaped by our need to fit reality into frameworks we can understand, but that doesn't mean the universe operates according to our intuition. When it comes to nature, there are only a few things we can directly observe: particle properties like position, momentum, scattering amplitudes, and quantum states. The rest is interpretation, an attempt to map the unknown onto what feels familiar, assuming that the underlying nature of reality aligns with our expectations might be the wrong approach entirely. Instead, the rules governing the universe could be so alien to us that they defy not only our logic but even our ability to conceptualize them. Our perception, shaped by the limits of our senses and tools, might only ever reveal a fraction of what truly exists. As Neil deGrasse Tyson once stated, the universe is under no obligation to make sense to you. There's a particular misconception, often stated with absolute confidence, that we have no idea what consciousness truly is. This belief, however, is misguided. a byproduct of centuries of philosophical and scientific debates that have clouded our understanding. The truth is, we know exactly what consciousness is. It's everything else that we are unsure about. Don't believe me? I propose you conduct an experiment. Try answering this question. What exactly is time? Perhaps you would begin by defining time in terms of motion, like the ticking of a clock, or maybe in terms of cause and effect, one event following another. But then, what is motion? What is causality? If you continue down this path, you'll find yourself caught in a never-ending spiral of definitions and questions. Sooner or later, you'll circle back to the original question: what is time? No matter how hard you try, you'll end up trapped in a loop, unable to reach a final answer. That is, of course, until you bring consciousness into the mix. You see, time is something we experience, a sensation of sequence and change that arises in our minds. By grounding the concept in our awareness, we break free from the endless loop and begin to make sense of it. This highlights a crucial yet often overlooked point. Physics wasn't designed to describe an external, objective world as it exists independently. Instead, it was created to explain how what we call the objective world is experienced by conscious beings like us. At its core, physics is a detailed system of mathematical models that connects various external concepts, enabling us to predict and make sense of our experiences. Conscious experience isn't just a side effect of science, it's a fundamental part of its framework. Without consciousness, the entire structure of science wouldn't hold up. So claiming to understand concepts like mass, energy, time and space while treating consciousness as an unsolvable mystery doesn't really add up. Why do so many hold such a belief? Perhaps it stems from centuries of academic tradition where consciousness was treated almost as a forbidden topic, too abstract, too subjective, and straying too far from the realm of measurable facts. The irony, of course, is that consciousness is arguably the concept we understand most directly. It is the very essence of what we are. Even without science or the intuitive tools that all living beings use to navigate the world, there is one truth we would still grasp: we exist. In 1931, one of the greatest scientists working in the new field of quantum mechanics, Max Planck, said, "I regard consciousness as fundamental. I regard matter as derivative from consciousness. We cannot get behind consciousness. Everything that we talk about, everything that we regard as existing, postulates consciousness." Hopefully, this makes the point clearer. It's essential to recognize the central role consciousness plays within the mathematical framework we call science. Planck's statement implied that our understanding of the physical world and existence is inherently linked to our conscious experience. The idea that consciousness doesn't exist or is somehow beyond our understanding is a fundamental misunderstanding. Consciousness is not just a part of reality, it is reality itself, and it's not some elusive mystery. It's something we all inherently know and experience directly. So, where does our conscious experience come from? It's pretty straightforward. It comes from the stuff we're made of. Right now, as I sit here writing and reading this video script, laptop precariously balanced on my lap, I'm struck by a profound yet simple truth. I'm a physical, natural being, a collection of biological processes and molecules. My consciousness isn't some mystical separate identity, it's an essential part of this physical me. It's not apart from what I am, it is what I am. Let's take this a step further. Can we really say for sure that non-conscious stuff exists? Think about it. I look around and yeah, my chair seems pretty lifeless, but I can confidently say there's not even the tiniest flicker of consciousness in it. Not really. That's the whole idea behind panpsychism. The belief that everything, even the stuff that looks completely inert, might have some basic level of consciousness. I'm not saying my chair is out here reflecting on the meaning of life, but at a fundamental level, and since everything is made up of the same subatomic stuff, there might be some tiny spark of experience embedded in it. Why even consider this? Because it simplifies things. It neatly ties together the one fact I'm absolutely sure of, that this physical being sitting here, me, is conscious. Hold up, don't rush past this just yet. Of course, you could argue that non-conscious stuff exists too, but if you do, there's a big question you'll need to answer. Here's the deal. We know conscious stuff exists, right? Now, if you're saying there's also non-conscious stuff, you're claiming two entirely different types of stuff coexist. So, how do you explain how humans ended up with the conscious kind while, say, a table didn't? How does that separation even work, bearing in mind that everything is made up of the same subatomic stuff? Postulating two separate kinds of stuff, conscious and non-conscious, makes things way more complicated than they need to be. It's a leap you shouldn't take without strong evidence, and in this case, there isn't any. Just because the atoms in a chair don't display the kind of consciousness you experience doesn't mean they lack the fundamental properties needed to create consciousness. And don't forget that the same basic building blocks, the atoms and their interactions that make up the chair, also make up you. The truth is, we don't fully understand how these properties come together to create the rich, subjective experience of being alive and aware, but your very existence is proof that they can and they're real. Now, before you start asking if your chair is conscious, let's clear this up. Not every bunch of atoms forms a thinking, self-aware being. Sure, the atoms in the chair might have some basic level of consciousness, but they don't combine in the way needed to create awareness. It's no different than how not every lump of carbon becomes a diamond. The right conditions are key. And speaking of the right conditions, doesn't the brain seem like a perfect candidate for something capable of producing a unified, complex consciousness? We'll get into that soon, but let's take a moment to recap. We know consciousness is real, we understand what it is to an extent, and we have a pretty good idea of where it comes from at least. The next big question is, how does it turn into the rich, vivid experience we, and likely other animals, have? We're still trying to understand what kinds of arrangements of matter lead to a unified consciousness like ours. To put it simply, we're asking why some things, like humans, are clearly conscious, while others, like chairs or my laptop, don't seem to be. The brain is the most likely answer. It's the key factor that distinguishes beings with obvious consciousness, like us, from things that appear inanimate, like chairs or an empty cup. There are several promising theories that attempt to explain consciousness, with integrated information theory, IIT, and orchestrated objective reduction, OR, being two of the most discussed. These ideas might hold some answers, but we're not there yet. What's clear is that understanding consciousness will require more research and more experimentation. Orchestrated objective reduction, a theory proposed by Roger Penrose and Stuart Hameroff, suggests that quantum entanglement, a phenomenon where particles are connected in such a way that the state of one affects the other, even over large distances, might be happening within microtubules of brain cells. According to OR, this quantum entanglement within the brain could play a role in generating consciousness. However, this theory has faced a lot of skepticism. Critics argue that the brain's warm, noisy environment isn't ideal and is far from the isolated, ultra-cold conditions typically required to sustain quantum coherence, a necessary component for entanglement. But supporters of this theory counter that it's not about brains being indefinitely and universally entangled. Instead, they propose that the brain functions as a dynamic, temporally entangled system, with coherence occurring in bursts that are sufficient to produce conscious experiences. They point to emerging evidence that biological systems, including photosynthesis and certain enzymes, appear to exploit quantum effects even in seemingly unfavorable conditions. Integrated information theory developed by Giulio Tononi takes a different approach, focusing on how information is processed and shared within a system. According to this theory, consciousness arises in systems that are highly integrated, meaning that they share a significant amount of information across their parts. The theory even provides a mathematical framework for measuring the level of consciousness in different systems, offering a way to compare and quantify conscious experience. While both theories have their critics and neither is universally accepted, they open up fascinating possibilities for understanding the nature of consciousness. Whether it's quantum processes or information integration, or perhaps something else entirely, each theory brings us a step closer to unraveling this profound mystery. Here's the key takeaway. We already have a clear path forward. By embracing our natural existence and the conscious experience that defines it, the next steps become straightforward. Build, test, and refine. This involves creating various configurations of matter, studying them closely, and looking for signs of consciousness. It's the scientific method in action, guiding us closer to uncovering the secrets of this remarkable phenomenon. This morning, I started my day with a cup of black coffee and a simple slice of buttered toast. Nothing fancy, just the usual. I could have gone for cereal or maybe skipped breakfast entirely, but I didn't. I had toast. Interesting, right? Who cares what I ate for breakfast? It's just a mundane detail of my day. But what if I told you the universe might care? Now imagine after breakfast I head to the lab to run some quantum physics experiments. These experiments should, logically, depend on what I do in the lab, how I set up the equipment, the measurements I take, and so on. Why would the outcomes of those experiments have anything to do with what I ate for breakfast or the weather outside, or even the latest football scores? It seems strange to even suggest it. Laser beams bouncing through mirrors and crystals should have nothing to do with the small details of my morning, or at least that's what we'd assume. The conditions under which an experiment takes place are known as its context. In practice, the contexts we focus on are usually limited to specific settings on the equipment in the lab. But maybe other factors matter too, like the room's temperature, whether the lights were on or if the door was left open. Especially when things go wrong, and they often do, it's natural to look at the context for clues. Still, some parts of the context seem so unrelated that they couldn't possibly affect the results, like my breakfast, for example. A theory is a set of mathematical rules that predicts the outcomes of experiments. Most theories naturally exclude irrelevant contexts by not addressing them. Other dependencies are ruled out through experimentation. If there's no possible setup in the lab that can differentiate what I had for breakfast, then the theory has no reason to reference it. It's a practical application of Occam's razor, and as you'd expect, quantum physics doesn't concern itself with breakfast choices. As powerful as quantum physics is, it's still just an operational theory. Think of it as a detailed lab manual, one that provides instructions for preparing experiments and predicting outcomes. It's incredibly precise, enabling us to create technologies that underpin modern life. But it doesn't offer any insights into the nature of reality itself, and that's something that bothers many physicists. What is reality? Nah, let's not start with that. But instead, let's focus on scientific realism. The idea that a world exists independently of any mind that perceive it. Scientific realism suggests that this world is slowly uncovered through the progress of science. It's the belief that the true nature of reality is something science investigates. And while we may never fully understand it, each experiment brings us closer. This view is widely accepted among scientists and science enthusiasts alike. For example, a typical scientific realist might believe that fundamental particles, like electrons or quarks, are real, even though we can't directly observe them with our senses. These particles, along with their properties, are thought to be part of the state of the world. A more ambitious version of this view holds that the state of the world can be fully described using mathematical quantities that obey equations we call physical laws. From this perspective, the ultimate goal of science is to discover these laws. But how does quantum physics fit into this? As mentioned earlier, quantum physics isn't a realistic model of the world in the traditional sense. It doesn't describe states of the world in terms of definite quantities. Instead, it deals with probabilities and potential outcomes. This raises an obvious question: can we extend or replace quantum physics with a deeper theory that specifies these real states of the world? This is the question Einstein first asked with colleagues Podolsky and Rosen, making headlines in 1935. The EPR paradox was a thought experiment designed to challenge the completeness of quantum mechanics, the concept of entanglement. Einstein and his colleagues argued that quantum mechanics could not provide a complete description of reality. To explain these seemingly paradoxical results, Einstein and his colleagues proposed the existence of hidden variables. These hypothetical variables would determine the outcome of quantum measurements, providing a more complete and deterministic description of reality. In essence, they believed that quantum mechanics was incomplete because it failed to account for these underlying yet unknown variables. The hypothetical real states of the world came to be called hidden variables, since an experiment does not reveal them, at least not yet. Over the decades, quantum physics evolved into an applied science, and its foundational aspects were largely set aside in favor of practical recipes found in textbooks. These textbooks, many still in use, haven't changed much since the mathematical framework was established nearly a century ago. However, in the 1960s, a groundbreaking discovery called contextuality emerged, fundamentally challenging the concept of an independent reality. This discovery, formalized by the Bell-Coken-Specker theorem, placed serious restrictions on scientific realism. The most famous contributor, John Bell, demonstrated that quantum physics inherently includes non-local correlations, a phenomenon tied to quantum entanglement. This means that entangled particles can influence each other instantaneously, regardless of the distance separating them. This violates the principle of locality in classical physics, where influences are limited by the speed of light. While non-locality gained fame through experiments involving quantum teleportation and cross-continental entanglement tests, it's just one aspect of the broader concept of contextuality. Contextuality at its core posits that the reality underlying quantum physics isn't absolute, but depends on the context in which it's measured. In other words, the properties of quantum systems don't exist in isolation. They are tied to the specific experimental setup used to observe them. For example, two different ways of mixing laser light can result in completely indistinguishable outcomes, regardless of how advanced your equipment is. Quantum physics only cares about the resulting mixture, not the specific process used to create it, an application of Occam's razor in action. This implies that the universe itself may operate by streamlining reality, discarding superfluous details, and presenting us with only the observable and verifiable aspects of a system. Now, imagine attempting to formulate a more fundamental theory of reality that underpins quantum physics. To uphold Occam's razor, such a theory should ideally rely solely on observable contexts. However, quantum mechanics itself precludes this possibility. As demonstrated by both rigorous mathematical proofs and compelling experimental evidence, quantum mechanics inherently exhibits contextuality. This means that measurement outcomes are influenced by the specific experimental setup, even when these setups appear identical in terms of their observable properties. Does this mean the universe cares about what you eat for breakfast? Not exactly. But it does mean that if you want to insist the universe doesn't care, you must also abandon the idea of an independent reality. Contextuality forces us to accept that reality isn't something that exists out there, unchanged and objective. Instead, reality depends on the way we choose to observe it. I know this video might feel like a lot to wrap your head around. We've dug into some pretty wild ideas. How quantum physics doesn't just tweak what we know about reality, but completely rewrites the script. Contextuality isn't just a fancy word buried in textbooks. It's at the core of how the universe operates. It tells us that the results of experiments and even the properties we think objects have are not intrinsic but are tied to the way we observe them. In essence, contextuality implies that the universe doesn't simply present itself to us as a pre-existing objective reality. Instead, our interactions with the universe through the process of observation actively shape the reality we perceive. This challenges our classical intuition and forces us to rethink what it means for something to exist. Think about that for a second. The idea of an independent, objective reality, a world that exists the same way whether we're watching or not, just doesn't hold up in quantum mechanics. Reality, as strange as it sounds, depends on us. It's shaped by the context we create when we measure or interact with it. That's not just a shift in the rules, it's a complete change in how we understand the universe. So, what's the takeaway? Honestly, we still have so much to figure out. Quantum mechanics has opened the door to questions we didn't even know we should be asking. And yeah, it's a bit unsettling, but isn't that also kind of amazing? The fact that there's still so much mystery left in the world? That's why I love talking about this stuff. It's not just about answers, it's about curiosity. If you're still here thinking about all this, then you're already part of that journey. And who knows, maybe the next big discovery that reshapes everything could come from someone like you. Thank you for watching this video. Also check out this video on your screen where we talked about how quantum computers breaks the universe.